Welcome back. Today I'll discuss a very tricky topic, and I've seen really good students, even really good students, facing problems while dealing with the questions based on these concepts. I'll primarily discuss three topics which are in continuation of the previous topic of distribution of induced charges. First, I'll discuss how the charge gets distributed on an irregularly shaped body. Let's say the body doesn't have a fine spherical surface, rather it has got a non-uniform physical surface, and I give some charge to it. Now on a sphere, it was easy to assume that charge get uniformly distributed on its surface. But what about this? Will the charge density at all places on its surface be same? The answer is no. To understand where the charge density would be more on this sharpish face or rather on this flat face, flat piece of that surface, where the charge density will be more. To understand that, I take a simple example. Let us assume that I've got two spheres connected by a conducting wire. I'm assuming that flow of charge from one to other or vice versa is allowed. I give this, let's say in equilibrium, this has got some charge Q and it has got radius R, and it has got some charge capital Q and its radius is capital R. So, if the system is in equilibrium, what should be the condition which I should start with? The basic thing is that they should have same potential. As you have got two water tanks, let's say these are two water tanks, one has got higher capacity and the other has got lower capacity. If you connect them through a pipe, how the water will flow and for how long it will flow? The water will flow from one tank to the other, or from this to this or this to this, as long as the water level in both the water tanks becomes constant. That means it's the water level which we refer to, which you can treat it as an analogy as electric potential. So if two spheres are connected and charge is flowing instead of water, so what quantity should be equated so that the equilibrium can be attained? That quantity is electric potential. If the system is in equilibrium, now no new charge is flowing from one charge to the other, one sphere to the other, that means that the potential of this smaller sphere is same as potential of this bigger sphere. Now what will happen? This means that 1 by 4 pi epsilon naught Q by R is equal to 1 by 4 pi epsilon naught capital Q by capital R. So Q by Q is equal to R by R. Let's see what is the surface charge density. Let's say it is sigma 1 and sigma 2, or you may call it sigma small and sigma big. What will be the charge density on these two spheres? What about sigma s over sigma big? This will be the charge on this, that is Q, divided by the surface area 4 pi r square divided by capital Q divided by 4 pi capital R square. So what do I get? Q by capital Q into R square by R square. Now Q by Q itself was R by R into R square by R square. A little simplification gives me R by R, which is definitely greater than 1 because R is the radius of the bigger sphere. This means that sigma small is greater than sigma big. The surface charge density would be more on a surface which has got smaller radius of curvature. That means surface charge density is inversely proportional to radius of curvature. That means sharper the edge, higher would be the charge density. This concept I would need in later part of this topic. So let's first of all settle this thing that at sharp edges the surface charge density would be higher than the flat surfaces. Now let us discuss a very important topic about cavities inside conductors. Cavities inside conductors. Let's say I've got a spherical conductor, but it's hollow from within. There is a cavity inside it. And I place some charge plus Q at its center. I know electric field inside the conductor is 0, but this space is empty. There is a charge and there is an empty space over here. What will happen? Will electric field be present over in this region, in this empty region, in the cavity region? Yes. Electric field will definitely be present. It will not be equal to 0. But if electric lines are originating, where are they terminating? If electric field lines are originating from Q, where are they terminating finally to make electric field 0 at this place? Obviously, the electric field lines are not crossing this region because this region is conductor and you don't have electric field lines in this region. So definitely they are terminating at the inner surface. So is there some charge on the inner surface? Yes, that's the induced charge. So now the problem is how much induced charge would be present when I place charge Q at the center of this cavity. To understand that, what I can assume, obviously as I am saying that field lines will go and they will be terminating at this point. So there is basically negative induced charge on the inner surface of this cavity, inner surface of this sphere, or you can say inside that cavity. But overall this conductor was neutral. There was no charge given to this sphere. The charge was placed inside the cavity, but charge was not given to this sphere. So when negative charge has appeared over here, some positive charge will appear on the opposite face. What this charge is, how much charge gets dwelt on the outer surface and how much charge gets induced on this inner surface. This is the question. Now, it is easy to understand this. For that matter, you can simply take a Gaussian surface over here. Inside the Gaussian surface, because this is conductor, so electric field in this region is 0. And E dot ds, if E dot ds is equal to 0, we know that electric field, this is equal to, that should have been equal to Q net by epsilon naught. That means Q net must be 0 to make electric field 0. And Q net is what? The Q induced, let's say I call that Qi. Qi plus Q should be equal to 0. The induced charge is just equal and opposite to the charge you have placed at that point, at the center of this cavity. So if you have placed 3 coulomb charge over here, negative 3 coulomb charge will appear on the inner surface. But what about the outer surface? What about this surface? Need not to tell you that since it was overall neutral, now again I am removing the Gaussian surface back just to make you understand. Now this is the overall this hollow sphere, or you may say a sphere with a cavity inside it. Now what will happen? Overall it was neutral. If Qi has appeared over here and let's say Qi dash has appeared on the outer surface, Qi dash plus Qi should be equal to 0 again. And that means Qi dash is equal to minus Qi. So Qi was equal to minus Q. So this becomes the outer surface will gain plus Q charge. The outer surface will gain plus Q charge. This is really interesting. Let's say the question says there is a conductor and there is a cavity. There is a cavity and inside the cavity a charge Q is given. Charge Q has been placed. So what will happen? This Q will not matter. Actually, plus Q will appear at its outer surface. And if you wish to find out electric field at some point, you just treat it as point charge. This conductor is basically playing no role when I am looking at it outside, from outside the sphere. What is happening inside the sphere, you don't understand that. The outer world will not be able to understand that. But this is okay. Now electric lines are going radially like this. This is a oversimplified version. What if charge is not placed at the center? Rather, it is somewhat placed asymmetrically. Let's look at it. This is the cavity. Now the charge is placed near one face, near one surface. Let's say plus Q charge is placed over there. How much induced charges would be there in the inner surface? How much induced charges would be there on the outer surface? And secondly, what would be the form of electric field inside this cavity? The answer is yes. Since plus q charge has been placed, the negative charge will again appear on this inner surface. But since plus is placed close to this surface, negative would be more crowded in this region. Negative charge would be more crowded in this region than in the region which is away from it. The induced effects obviously would be higher on the surface which is closer to the given charge plus q. So electric field in this region would be stronger, and you know electric lines always hit the metallic surface perpendicularly, so they remain perpendicular like this. They'll always be perpendicular, and they'll also hit like this. They'll always be perpendicular. But electric field would be weaker in this region than in this region. But the total charge, if Q is given in has been placed inside the cavity, the induced negative charge would always be minus Q, and you can again say that prove that by assuming a Gaussian surface over here. Q net would be 0. It's easy to prove that. But what about the outer Q? Since it has been placed close to one surface, will the the induced charges on the outer surface would be uniform or non-uniform? I hope you have conveyed the question. Think over it again. The problem says, I repeat, there is a cavity inside the conductor. We have proven that if you place charge plus Q over here, the negative charge will appear on the inner surface of this conductor, and that will be equal to minus Q, and due to that minus Q, an outer surface will gain a charge plus Q. This is okay when I am considering this charge Q to be placed symmetrically right at the center. What if I don't place it at center? I have placed it asymmetrically. Now what will happen? Now again the magnitude of negative charge induced would be same, that is minus Q, and electric field will be stronger in this region. Electric field would be stronger because this charge is closer to this surface, so higher negative charge density is present in this region, but it will be weaker in this region. Electric field would be weaker in this region. But what about the distribution of induced charges on the outer surface? The answer is the outer charges would still remain uniform irrespective of position of this charge. I repeat, the charge will remain uniformly distributed on the outer surface. Charge would remain uniformly distributed on the outer surface of the conductor irrespective of position of the charge inside the cavity. Can you prove that? It is easy. Because you can again take a Gaussian surface. Whatever field was there, this is net field in this region is 0. That means the flux lines, whatever those flux lines were there, they are getting terminated right over there. So the effect of that inner cavity is not visible as long as its position is concerned. That the effect of the position of that inner charge would not be visible on the outer surface, and outer surface charge would remain uniformly distributed provided the surface is uniform. Now, if I take the outer surface to be non-uniform, this is the third case now. The first case was that the charge, the sphere, the conductor is spherical, the cavity is spherical, and charge is right at the center. That's an oversimplified version. Now the second case, I displace that charge from the center and place it asymmetrically. Even then, the charge on the outer surface remains uniformly distributed. Now the third case is if the conductor shape is irregular, like that. I have got a sharp edge over here, and I have got flattened regions in this portion, and there is a cavity, and I have placed the charge asymmetrically. Now what will happen? Minus Q charge will appear. That will be non-uniformly distributed. Remember, this negative charge will be higher, closer on the wall which is closer to charge Q, and it will be lesser in the region which is farther away from that central charge. But what about the outer charge? What about the outer surface? The total charge on the outer surface would still be plus Q. but it would not be uniformly distributed now because the portions which have got lower surface, lower radius of curvature, they'll have higher charge density, as I proved in the earlier part of the lecture. So this is very important about conductors and cavities inside conductors and charge distribution inside and outside that cavities. Now there is one more very important category of questions about distribution of charges. Let's discuss that. I'll start from a very simple example and then I'll keep on increasing the degree of difficulty. I hope you'll follow. Let's say I've got a plate and I gave it charge Q. Some of the charge, this is a conducting plate, some of the charge will go on one side of the surface and some other charge will go onto the other side of the surface. You may ask me what is charge on this region over this region. I am assuming it to be a thin plate and thickness to be almost zero. Even if the thickness is zero, still the plate will have two surfaces. One surface on one side and the other surface on the other side. And still, for theoretical purposes, I can consider a point right in between there. So, this has been shown just to understand the concept, a bigger magnified version of the plate. But in your mind, you should keep that this thickness is zero. Practically zero. Now, how the charge will get distributed on these two plates? It is easy to prove. Assume a point right in the center. Let's say this point is P. What is the electric field at this region? Since this is inside the conductor, the electric field is zero. I'm assuming, let's say, charge Q, let's say charge X goes on to this plate. Sorry, this was positive again. Total plus Q charge has been distributed. And Q minus X charge lies on the other plate. Because the sum of these two charges has to be Q. Now, we know that electric field due to a charged plate is equal to sigma by 2 epsilon naught. So, what is the electric field in this region due to this surface? It will be sigma by 2 epsilon naught. And what is sigma? Sigma is basically charge over area. A is the area of the plate. And electric field due to this plate would be in the opposite direction. So, I can take it minus Q minus X divided by 2 epsilon naught A, and that has to be 0. Just cross multiply, and what do you get? X minus Q plus X is equal to 0. So 2x is equal to Q and X is equal to Q by 2. So charge get equally distributed on both the surfaces of this plate. This is not difficult, but this is the approach which will follow even in the complicated questions. So this is how we should follow. We should find out electric field at a point which is right there inside the conducting plate, and then we would be able to find out what is the net electric field in that region. And net electric field is obviously 0, and you get an equation, and you can solve that equation to find out the value. I take another example, a very important example. Let's say there are two plates. Instead of one, there are two plates. And I have given charge Q1 to this and Q2 to this. What would be the charges at this plate and this plate? We are normally more interested in finding out charges on the inner plates, because in many questions you would find that the outer plates, outer surfaces would be grounded. So that complicates the things and in some way simplifies it as well. We'll come to that, those kind of questions later on. But for the time being, it's just a suggestion that we are more interested in finding out charges on the inner faces. But anyhow, we'll be finding out all the charges. Let's say charge on this is Q1, charge on this surface is Q2, charge on this surface is Q3, and charge on this surface is Q4. Need not to tell you that Q1 plus Q2 should be equal to Q1. Q1 plus Q2 should be equal to capital Q1, and Q3 plus Q4 should be equal to capital Q2. These are two fundamental things. The charge on an isolated plate cannot be cannot be changed. Now, you may think from the previous example, okay, Q1 get distributed equally. No, now this time charge cannot be equally distributed because there are some other charges also which will create some effect inside it. Think of it. Consider a Gaussian surface like this. I am considering a Gaussian surface. Over here, electric field is 0. Over here, electric field is 0. And if electric field is going in this direction or in this direction, I don't know in which way the electric field is. I really don't know. So it may be either in this direction or in this direction, but in whichever direction it is normal to this surface. It is along the surface, so perpendicular to the normal to this surface. This means that flux through this is 0, flux through this surface is 0, flux through this surface is 0, flux through this surface is 0. That means E dot ds is equal to 0, which is equal to Q net divided by epsilon naught. That means Q net is equal to 0. That means whatever charge is there, whatever charges are there over here, and whatever charges are over here, I don't know which of them is positive, which of them is negative. I am ignoring that fact. So Q net is 0. This means that Q2 plus Q3 should be equal to 0. That means Q2 should be equal to minus of Q3. So I can now say, okay, let's assume Q2 be positive, then Q3 would be negative. It will be equal and opposite to that thing. And from here you take a very, very important, you may say a corollary, a result, a crux. While doing questions, when two plates are placed, I'll tell you how to calculate charge on the outer surfaces in the next portion. But keep this thing in mind that charge on the inner faces would always be equal and opposite. Charges on equal inner faces would always be equal and opposite. Every time you don't need to solve these things, to prove these things. While doing multiple choice questions, you won't be having enough time while sitting in a competition. So what you need to do, you should remember this thing. What? That charges on the inner faces are always equal and opposite. Now let's see, what about Q1 and Q4? That's also we need to calculate. What about electric field at this point? Let's say point P, as we did in the case of first plate, a single plate. Now there are three fields in one direction and one field in the other direction. Let's say Q1 is pushing it in this direction. So this electric field is in this direction. But electric field due to Q2 on this surface would be in this direction. About Q3 would be in this direction, and Q4 that would also be in this direction. But net electric field is 0. So sum of these three electric fields must be equal to this electric field. Let's proceed with it. So what is electric field to Q1? That is the denominator is going to get cancelled out ultimately because every time you will get the same denominator. So I am just writing down as Q1 by something, that would be equal to what? Q2 plus Q3 plus Q4. Q2 plus Q3 plus Q4. But you know that Q1 was equal to Q3. Oh, sorry. Q2 was equal to Q3. So Q1 is equal to Q4. Q1 is equal to Q4. So whatever charge is over there, the same charge will appear on the outside, on the other side of the second plate. On the other side of the second plate. Now, what are the relations of Q1, Q2, Q3, Q4 with respect to Q1 and Q2? To do that, what you can do? You can add these two equations. Q1 plus Q2 is equal to what? Q1 plus, that will be equal to Q1 plus Q2 plus Q3 plus Q4. But Q1 and Q3 are equal and opposite. Q2 and Q3, sorry. Q2 and Q3 are equal and opposite, and Q1 and Q4 are equal. That is equal to 2 times Q1 plus Q2. So Q1 is equal to Q1 plus Q2 divided by 2. The charge on this case would be what? Q1 plus Q2 by 2. And same charge would appear on this plate. Q1 plus Q2 by 2. and to find out Q2 and Q3, you can simply subtract them. So what would be Q2 minus Q1? Q2 minus Q1 would be Q3 plus Q4 minus Q1 minus Q2. This time Q4 and Q1 get cancelled out, and Q2 is basically minus Q3, so you basically get 2 times Q3, Q2 minus Q1, so Q3 equal to Q3 is equal to Q2 minus Q1 by 2. And what would be Q2? Q2 is negative of that. Q2 would be Q1 minus Q2 divided by 2. So on this surface you will have Q1 minus Q2 by 2. On this surface you will have Q2 minus Q1 by 2. On this surface we have already calculated Q1 plus Q2 by 2, and on this surface it will be Q1 plus Q2 by 2. So this was the case of 2 plates. Can you do a question in which there are 3 plates? This is an assignment for you. Try this question. You can solve it generally as well, but I am giving you a numerical problem. It would be mathematically little simpler to deal with lesser number of variables. So I am taking it Q, it is minus Q, it is 3Q. Find out charges Q1, Q2, Q3, Q4, Q5, Q6. And it would be interesting to find out electric field as well at point A, B, and let's say 2 are enough. Once you will be able to find out the surfaces, charges on each surface, and you are asked to find out electric field, you can use the formulas which we have already developed using Gauss theorem directly. Then you don't need to calculate, at this point you don't need to calculate electric field due to this surface and due to this surface. You can treat it as whole having charge 3Q. I hope you will post the answers after solving this. These topics are extremely important and tricky, and I've seen really good students even failing to deal with these topics. Thank you.